Welcome to Quick Learning. We will continue the previous presentation on the topics of operational excellence like Six Sigma, Lean. So just for a recap, I will redefine the examples of Lean and Six Sigma, and I'll try to explain their meanings. So Six Sigma is the reduction of variation in any process, and lean is the reduction of wastages in any process. And further, we learned the 8 types of wastes that can be available and can be present in any system, and which lead to the non-valuable activities in the system. So, moving forward, we will discuss the types of variations. There are certain common causes of variation, and in these common causes, the variation can be inherent in any system, and there can be some common causes of variation, and these can be stable, predictable, and these are in control. So these common causes of variation are always stable, predictable, and are in control. And the other type of variation is due to special causes. These are special, specific, and assignable causes, and the factors that induce variation over and above that inherent to the system. Process with common causes plus special causes are unstable, unpredictable, and not in statistical control. So in the picture here you can see the above graph where we have some variation in the process, but it is controllable and it is predictable. While in the graph downside, you can see at one place there is the variation that is very high, and this variation is due to some special cause, and this cause is unpredictable and this cannot be controlled proactively. So these are the two types of variations in any system. So going back to Six Sigma process, we will show the plotting of data in the form of a bell curve. You can see that in this graph our data is in the form of bell curve, starting from lower specification limit LSL to the upper specification limit USL. So in the middle, that the dashed red line, this is the mean, and moving on the right side and on the left side we have this standard deviation. So if our data complete 99.9997% of the data is between these two six standard deviations, then we will say that our process is a Six Sigma process. That is, it is fit for customer's requirement. If our 99.99% data and or the product specifications are inside these six standard limits on either sides. But there is another case. Here you can see that uh, our data, if we make these USL and LSL a bit narrower, and we say that the data is between 3 sigma on both sides, then the three standard deviations on the both sides, then this data is the 3 sigma data. So here you can easily understand that what is sigma. Sigma is actually the standard deviation number. If data is between six standard deviations, we will say it's 6 sigma, and if data is between 2, 3, 4 standard deviations on both sides, then this is 2, 3, 4 sigma. So here is the benchmarking of the where we can see the sigma number, the yield of the process, the defect per million, and the type. So you can see that starting from number 6, in the Six Sigma process, our data is 99.999% stable and accurate, and the defects per million is 3.4, means 3.4 defects are available in 1 million samples. So that type of data or the process is a world class process. Similar for 5 sigma, the data is 99.97%. The defects per million is 233 now. and this also comes in the category of world class data. Now going down, we have 4 sigma and 3 sigma, where you can see that yield is going down. On 4 sigma it's 99.3 and on 3 sigma it's 93.3. Consequently, the defects per million is getting increased. For 4 sigma it's 6210 defects per million, and for 3 sigma it's 66,807 defects per million in the product. And this type of process is called as a better process. And the typical process is 1 and 2 sigma, where data yield is very low at 69% and 13.9% respectively, and the defects per million are very high, 308,000 defects per million for 2 sigma and 691 defects per million for 1 sigma, and this is the typical process. So here you can see that the sigma scale of Meyer is perfectly correlated to such characteristics as defects per unit, parts per million, and probability of failure or error. So this is the table that shows us the significance of the variations in any data, and it is linked to the stability of the process, stability of the product characteristics. So we have to try in operational excellence that we have to remove the variables, or we have to reduce the impacts of the variables, so that our system can go towards minimum variation and towards higher sigma value. So thank you so much.